I'm in class. Are you going soon? I'm in class. Yeah. No. Oh, I.
Question about which chapter this is. This is covering now the second half of chapter 4. This is a two-part lecture, so I'm going to finish this lecture today on chapter 4, and then we might have time to start in on the next chapter on light. Are there any other questions before we get started? Remember, you should be checking the Mastering Astronomy website for homework. You should be checking D2L for the weekly quiz. Some people haven't done the quizzes. They're worth 50% of your overall grade. And remember, I try to make it easy on you. If you miss one by accident, or even two, I drop the two lowest quiz grades at the end of the semester. But make sure you check every week. There's a quiz in D2L. All right, well, any questions? So where we left off, we were talking about conservation laws. These are laws that allow us to solve complicated problems in physics, or at least that otherwise would have been complicated. But there's a great simplification due to the conservation laws. We have a bunch of billiard balls or planets orbiting around them. You look at them at one point, there's this thing you can calculate called momentum, mass times velocity. You add up all those momenta, the total momentum is always the same. Conservation of momentum. Same thing for angular momentum. That's mass times velocity times distance from the center of rotation. So if you're orbiting, conservation of angular momentum, that stays the same. And then conservation of energy. And last time we talked about angular momentum. So for example, the Earth around the sun. That's an example where conservation of angular momentum applies. If you multiply the distance from the Earth to the sun times the Earth's mass times its velocity, that always stays the same. And as a consequence, and this applies to any planet. So as a consequence, this is another way of looking at Kepler's second law, that if you're further away from, say, the sun, you have to slow down because your distance is larger. If angular momentum is going to be conserved, stay the same, and if you get closer to the sun so that your distance r is smaller, your velocity has to go up. So you whip around if you get closer to the sun. We gave another example of conservation of angular momentum, right? Maybe just more familiar to you. If you're spinning around in an office chair or you're skating, if you have your arms stretched out, that's a large r, large distance from rotation. But if you pull your arms in, angular momentum is conserved. So if that r gets smaller, the velocity has to get larger. So you spin around faster, right? So we're talking about either a large r and small v or small r and large v. Either way, this quantity called angular momentum stays the same. It's conserved. This is one way of thinking about, say, the orbits of planets or all sorts of other phenomena, such as figure skating. Okay, and last time I also introduced the concept of energy. So this is just this quantity that has lots of different forms. We'll talk about energy in motion, called kinetic energy, stored energy, or potential.
Go away!
We'll even talk about class. There's energy in mass itself, and you can, and this is this quantity that we've discovered is conserved. If you add up all the different kinds of energy, it always stays the same, and it can transform from one to the other. Right? You can get light energy to grow plants, and then the plants store in potential energy. It locks that energy in chemical bonds. Then you eat the plants and you store it as calories and chemical bonds and your fat and calories, the way your body stores that energy. Then you can burn that energy, turn it into kinetic energy, whether you ride a bike, or we do the same thing with gas in our automobiles. And then it turns into heat. So that's a form of thermal energy, energy in motion again, kinetic energy, but on the level of molecules. And things that are hot radiate light. So all these forms of energy are all, if you add it all up, it's all conserved, but it can transform between different kinds. And one of the really cool applications of this is understanding heat and temperature, that something that for thousands of years people thought, they didn't understand what it was, but they thought it might be its own thing. Like there's this thing called heat. Things can be hot or cold, right? But now we understand it. It's a type of energy. It's specifically a type of kinetic or motion energy that we call heat or thermal energy, associated with vibrating and fast moving particles. So gas, if a gas, in this room, it feels warm right now, that's because the gas molecules are vibrating and moving quickly. And if you heat it up enough, you learn all sorts of interesting things, right? If you heat up any object, things start bumping around faster to the extent that they start destroying things, right? That's why you get burned. Similarly, they bounce around faster, they push against things. So, if you heat up the air in a balloon, the balloon expands. Okay, so we've learned a tremendous amount about things just by understanding that temperature, which is a measure of how fast these molecules are moving, means that things have a higher thermal energy or energy in microscopic motion. Okay, so this is one type of energy, and there's different scales for measuring temperature, basically how fast at a microscopic level atoms are vibrating and moving. And in science, we tend to like the Kelvin and Celsius scales the best. Kelvin is great because if you realize that temperature is related to microscopic motion, you might realize that there must be some zero, right? If things stop moving, that should correspond to zero. So the Kelvin scale shown on the left is the scientific scale we use, where zero corresponds to the lowest possible temperature. Okay, but we're a little bit more familiar with the Celsius scale. Luckily, Celsius is the same as the Kelvin scale, but all shifted by 273 degrees, so that what we call absolute zero in Kelvin is minus 273 degrees Celsius. Now, the Celsius scale was originated because 0 corresponds to the freezing point of water, and 100 corresponds to the boiling point of water. And that's great. That's very useful, two useful quantities. But on the Celsius scale, absolute 0 is not 0. It's minus 273 degrees. And that on the Kelvin scale is reflected by that being the lowest possible temperature, 0. Here in America, we use Fahrenheit a lot, which we don't like in science so much, but it's just something you have to be familiar with and how to translate between them. So on Fahrenheit scale, 0 degrees, the freezing point of water is 32 degrees, right? You probably know that. And boiling point of water, 100 degrees Celsius, corresponds to 212 degrees Fahrenheit. Now this originated because the Fahrenheit scale originated because on the Fahrenheit scale, 100 corresponds to roughly body temperature. Right now we say 98.6 degrees about, but at the time, 200 years ago, the best they thought was about 100 degrees Fahrenheit. So that's where it came from. Okay, but now it's not quite as useful because it's hard to remember 212 degrees for the boiling point of water, 32 degrees for the freezing point of water, and absolute 0 is minus 459 degrees Fahrenheit. Anyways, these are the three main temperature scales that you'll find. In astronomy, we tend to use Kelvin. So the absolute lowest temperature you can ever get is 0. That's what's so useful about it. But on that scale, then the freezing point of water is 273 degrees, boiling point of water is 370 degrees. Okay, sometimes we'll also use Celsius. Okay, so this is an example of a question I'd like you to know. What is absolute 0? What do we mean by that? The lowest possible temperature, 0 degrees Kelvin. And one thing to remember about temperature is that temperature it tells you how much little microscopic motion there is, but it doesn't tell you how much of a substance has that temperature. And the more of a substance at a temperature, the more energy it has, right? So there's a difference between temperature and energy. So for example, a match, you can light a match and it's very, very hot, but you can lick your finger and extinguish the match. It doesn't burn you because it doesn't have a lot of energy. It's just a small amount of material that's at a high temperature, right? A similar example is the hot oven, right? An oven can be 400 degrees, but you can stick your hand in the oven. It doesn't burn you. That's because the air in the oven, while hot, doesn't have a lot of energy because there's not many atoms in the air. Whereas a boiling pot of water isn't as hot, right? It's just boiling. It's less than 400 degrees Fahrenheit, but nonetheless, it'll burn you very, very badly because there's more stuff in there. There's more thermal energy that it can transfer to your finger. Okay, so that's the difference between energy and temperature. The higher the temperature something is, the more energy there is per amount of the substance. But you need a lot of substance to have a lot of thermal energy. Another type of energy is potential and kinetic energy, right? So kinetic energy happens, say, when you throw a ball, right? It has motion. And why do we think of that as having energy? Because it can cause it could hurt you. If you get hit by a ball, right, it does stuff to you. But there's also the concept of potential to do that. The potential energy is if you throw a ball up in the air, eventually it comes to a rest before falling down again, right? So you throw it up with kinetic energy, then the kinetic energy goes away. It slows down as it gains potential energy at the top of its trajectory. And what does it have the potential to do? It has the potential to fall back down and gain kinetic energy. And the cool thing is that its energy is conserved here. You start out with just kinetic energy, but halfway through the ball's motion, when it reaches the top of its arc, no more kinetic energy. But energy is still conserved because that energy has been converted to potential energy. And then that potential energy gets converted back again into kinetic energy. And the whole time, the total energy is the same. Now, what happens when the ball hits the ground? Where does the energy go? Well, it goes into, when it hits the ground, it goes into heat and sound. Right, if you hit something hard enough, example is a meteor impact, which we'll talk about later, right? Then things get so hot it literally can heat up the atmosphere and burn everything, right? So that's an example of where all the energy is going. It can go in all sorts of directions and forms, but it's always conserved. Here's another example of potential and kinetic energy. If you put a mass on a spring, so a spring can store potential energy. You've all probably have an intuition for this. If you push a spring down, it's got stored or potential energy. If you let go, it springs back out and can actually hurt you, right? Or a rubber band, right? Stretch a rubber band, it has potential energy. If you let go, it can snap and generate a lot of kinetic energy. And a mass on a spring, it's constantly converting kinetic to potential. So you stretch out the spring, there's a lot of potential energy, you let go, the mass starts moving. So now there's kinetic energy. But then it compresses the spring, and now all the energy is potential energy. And then the spring pushes back out and it starts moving again. It has kinetic energy, back and forth, kinetic to potential energy. And what happens when it slows down and stops? Friction. Friction is the generation of heat. As it slides across the surface, it's generating heat energy. So that's where that energy ultimately goes. So one application that we'll see in this course, right, talking about astronomy here, is to this conversion between potential and kinetic energy is if you have a big cloud of gas. Okay? This is how stars form and our solar system formed. You got a big cloud of gas and it gravitates. Okay, we talked about Newton's law of gravitation last time. So it wants to contract under gravity. But when it does that, that potential has potential energy, just like a ball thrown up in the air. When it comes down, it starts speeding up, and that potential energy turns into kinetic energy. And so ultimately, this cloud of dust starts spinning It has to have kinetic energy. And also a lot of the energy has to go into heat. It has to heat up, right? So all that potential energy has to go somewhere. So it either goes into spinning and or heating up. And so the gas gets very, very hot. Okay? And eventually this will be the heat source that ignites the furnace of the sun. Okay, and we'll talk about that a lot when we talk about the sun. Another example of energy. So we talked about kinetic energy, potential energy. An example of potential energy was stored like caloric energy in plants and gasoline, thermal energy. Okay, there's also mass energy. MC squared. We'll see that this is what powers the sun. It's also what powers atomic bombs and nuclear energy reactors. And the idea is, okay, and this is, you could learn this through a whole course. So I'm giving you a basic description, but it's nonetheless correct, which is that mass itself has energy. And the famous equation that tells you how much energy is given by Einstein's E equals mc squared. So if you have a given amount of mass, there are ways to convert that mass into pure energy. And it's a huge amount of energy. How do you know that? Because the c in mc squared is the speed of light, and the speed of light is a huge number. So the amount of energy in a given amount of mass is a lot. Yet you square the speed of light and multiply it by the mass, and you get a very large amount of energy. Okay, so this is, as we'll talk about when we talk about the sun, this is the energy that powers the sun. This is why the sun is so bright and generates a huge amount of energy, right? We're far away from the sun, and nonetheless, you can get a sunburn, right? And that's that amount of energy is radiated throughout all of space, and only a tiny fraction of it, remember, is hitting the Earth. Okay, so the sun generates a huge amount of energy. Another example of this is the Earth is really hot when you go towards the center of the Earth. Why? Because there's radioactivity. There's basically a nuclear reactor in the center of the Earth that's constantly heating it up. Okay? So that's why you get volcanism and examples of the Earth being really hot. It ultimately comes from radioactive decay. That's also an example of energy being created by E equals mc squared. And we'll talk a lot about this when we have a dedicated lecture on the sun. But I do want you to be able at this point to explain, right? What does E represent? In this famous formula, E equals mc squared, it stands for energy, and it's the energy specifically stored in an object's mass. Are there any questions so far? Okay, in the case of the sun, where does that energy go? Well, it travels from the sun to us in the form of light. Light is another form of energy. It's a nice way of transferring energy from one place to the next. And you've probably felt that energy from a fire. The warmth you feel is mostly from infrared light hitting you. If you stand on a ladder, right, it takes energy to go up a ladder. So where's that energy from? Calories. That's stored energy in your body. And you create kinetic energy in your muscles to move yourself up the ladder. And you store energy, potential energy. So that's called potential energy. And you have the potential to fall, right? That's what the idea means, okay? The potential to fall, and if you fall, you speed up until you hit the ground. In which case you hit the ground, and where does your energy go? It goes into the heat and some sound waves. If you fall off a ladder, you gain motion, you gain kinetic energy. So that's an example of your potential energy, stored energy, being converted back into potential, back into kinetic energy when you fall off a ladder. Any questions about energy? We're going to be applying these examples in various ways as we talk about all kinds of astrophysical concepts. Now, the next thing I want to talk about is, we gave this whole history about heliocentrism versus geocentrism, and how You had this Copernican revolution and advocates like Galileo for it, and Kepler, who came up with Kepler's laws. It's really neat to understand that Newton's laws and Newton's laws of gravitation explain all of that. Okay? Newton's laws explain Kepler's laws, and we're going to move from just thinking about Kepler's laws to the more general understanding of Newton's laws that explains the motion of all matter, and it explains. I mean, it's a wonderful concept. It's kind of mind blowing when you realize, as Newton did, that the moon in the sky is just like a rock falling towards the Earth. It's just a big rock, and it gravitates. The Earth gravitates. Jupiter gravitates. The sun gravitates, and we're all just falling towards each other all the time. Now we keep missing each other, and that's what an orbit is. The moon is falling towards the Earth, but it's also moving, so it keeps missing us. That's what we call an orbit. So let's talk about, let's go recall Kepler's laws. Kepler's laws are correct, but they didn't have an explanation for them. So Kepler observed that the orbits of planets follow ellipses, okay, which are kind of oval shaped, which can include a circle, but they can also be like very stretched out, very elliptical. He observed the law of equal areas. That basically says that the further away you are from the sun, you go slower, and then you get closer to the sun, you whip around. And he had the harmonic law. This is the law of the period, how long it takes to orbit the sun. A year is, when squared, is proportional to how far you are from the sun. In other words, the further you are from the sun, what this tells you, you work that out to be that you orbit more slowly the further out you are from the sun. Okay, so this is what Kepler observed, and he came up with his laws, which are correct. Okay, but Newton discovered that this wasn't something just about things orbiting the sun. It's literally anything with mass attracts and can orbit any other thing with mass. So this was Newton's law of universal gravitation, discovered in or at least written down in 1687. And this is that there's a force between any two masses. Okay, take mass 1, say the Earth. Take mass 2, say the sun or the moon. There's a force between them that's proportional. Now, the constant of proportionality is capital G. It's called universal gravitational constant. I don't expect you to memorize that or anything. And the force is proportional inversely to the square of the distance. That means the force gets smaller the farther away you are, the farther these two masses are from each other. And it falls off pretty rapidly as the square of the distance. Okay. The masses are typically measured in kilograms, the distance in meters, and the force, the unit of force is in what are called newtons, right, after Isaac Newton. Okay, so according to the universal gravitation law of gravitation, this is sort of what I want you to remember about this, right? The force due to gravity is inversely proportional. That means the distance is on the denominator there, meaning the larger the distance, the smaller the force. That's what inversely proportional means. The force is inversely proportional to the square of the distance, meaning if you're twice as far away, the force decreases by 2 squared, or 4. If you're 3 times as far away, the force decreases by 3 squared, or 9. Okay. So here's an example of a question. So I'll ask this one, right? If you have so I'm giving you the equation here. Force is equal to constant times mass 1 times mass 2 divided by the distance d between them squared. If you increase that distance by a factor of 3, how does the force change? Okay. So think about it. You can either use this formula or just think in words about this last question. Inversely proportional to the square of the distance. Tell me. Okay, I have to bring up the poll here. Okay, tell me, the distance increases by a factor of 3. How does the force change? Distance increases by a factor of 3. What happens to the force?
It increased. Mm,
Someone said the question's not popping up for you. I'm not sure what to do about that. I mean, it looks like it popped up for most people. I'll give another 20 seconds just in case. It's just being slow. Okay, I will end the poll then. And wow, this is surprising. It literally looks like no one got the right answer. So I mean, this is good. We should discuss this carefully. So first of all, we can go back to let's go back to this previous question. According to this law of gravitation, the force due to gravity is inversely proportional to the square of the distance. What does that inversely mean? Well, it means, I think, what's intuitive about the force law. The further two things get apart, the force decreases, right? Larger the distance, the smaller the force. Okay. So that's the first thing we should establish here. And that's reflected in this formula that the distance is on the bottom, on the denominator. You have a larger distance between two objects. You have a smaller force, not a larger force. So if you increase the distance, as in this question, the force decreases, not increases. So that's the first thing to establish. The force decreases as you get further away. The second is to establish how much does it decrease. Is it a factor of 3? Is it a factor of 9? It's a factor of 9 because the distance increased by a factor of 3. D is squared, so it's 3 squared is 9. So the correct answer here was decreases by a factor of 9. The last answer. Are there any questions about that? All right, so Kepler had this law that said the period, take the period squared, right? Remember, that's a year for a given planet is called the period, how long it takes to orbit the sun. When squared is proportional to the average orbital distance cubed. So Newton not only derived this, but found that for different planets, different objects, that relationship has a different proportionality constant. And he derived what that was. Okay, so Kepler's third law is a specific case for the sun and the planets, but that can be applied to any two objects: the moon and the Earth, a whole galaxy and a star. And this is the more general law derived by Newton. And then another one, right, is Kepler's first law, the law of ellipses. So Kepler said the orbit of each planet is an ellipse, and we talked about that. That's an example of an ellipse is a conic section of a cone. So that's what I've drawn here on this picture. And Newton showed that this is true not just for orbit of planets around the sun, but around any two objects that are gravitating each other. So you put 2 pennies in space, I don't know, and they will slowly orbit each other in an ellipse. And examples of ellipses, or conic sections, I should say, examples of conic sections include the circle, if you slice horizontally, ellipses of various shapes as you slice sideways. Those correspond to most of the the planets in our solar system follow elliptical orbits, so they look like this shown in here. This, hold on, I need to reset this. Shown in green. But additionally, Newton showed that any conic section is an example. So another examples are parabolas and hyperbolas. If you slice even more vertically, this corresponds to things that are from outside our solar system. So if you have something from outside our solar system, it falls towards the sun and then slingshots back out. It follows a hyperbolic or parabolic trajectory, meaning it doesn't come back. It only comes in once and goes back out again. So again, Newton's laws are more general than Kepler's laws and apply not just to the planets, but to anything that's in the gravitational influence of anything else. Here's just some more examples of conic sections. So planetary orbits look like these: circular or more horizontal slices, more elliptical and more sideways slices. But then you can also include things that come from even outside of the solar system that follow these kind of vertical slices called hyperbolas. And so here's just showing what I mean. So these gravitational orbits can be fairly circular. That's an example of an ellipse. And most planetary orbits are indeed pretty circular, but they can also be very elliptical. In fact, a lot of comets, for example, as we'll talk about later, are very elliptical. They can go way far out so that we can't see them, and they slingshot around the Earth. And when they do, they get that nice plume as they get heated up. But then you can even have stuff coming from outside the solar system that are unbound. They're not bound to the sun. They just come in, visit for a little bit, and then slingshot back out. Okay, so these examples of gravitational trajectories. And we talked about Kepler's second law in terms of the way Kepler described it, in terms of the law of equal areas. We also saw that it was a consequence of conservation of angular momentum. Well, there's even another way of viewing it, through conservation of energy. Okay, as a planet gets further away from the sun, and again, doesn't have to just apply to the sun and a planet, it could apply to any two gravitating objects like the moon and the Earth. But if you get further away, you have more potential energy and less kinetic energy. The same way that if you go up a ladder, or you throw a ball up, it slows down, it gets more potential energy before falling back in, and it converts it back into kinetic energy or motion energy. So in the same way, if you have an elliptical orbit, a planet that's far from the sun is slow, and when it comes close to the sun, it speeds up. So that's a consequence of conservation of energy as well. And you see examples of conservation of energy all the time when you have things interacting in orbit. So here's just one example. You might have something that comes from, in a very elliptical orbit, like a comet coming from far in the outer stretches of the solar system. Okay, it comes towards the sun, and as it comes towards the sun, maybe it gets very close to Jupiter and exchanges energy with Jupiter. Now, energy is overall conserved. So suppose it exchanges energy with Jupiter so that Jupiter speeds up a little. Okay, so Jupiter gains energy. And you're not going to really see that in a change to its orbit because Jupiter is so much bigger than the comet that it's hardly going to nudge Jupiter. But now the comet has lost energy, so it can change into a different orbit that has, on the whole, less potential energy. See, because it doesn't get as far from the sun. So overall, it has less energy. Okay, so the comet slows down, it gets into a tighter orbit around the sun. This sort of thing happens a lot in our solar system. Energy is exchanged. Overall, it's conserved. Similar thing with a rocket ship, right? We can orbit the Earth like space shuttle did, or now say the International Space Station or any kind of satellite orbiting the Earth. It can hug the Earth tightly with not a lot of energy, but if you fire your rocket boosters, you can add energy, and the additional energy allows you to get further and further away from the Earth. So if you fired your rocket boosters here, for example, what would happen is you'd enter a more elliptical orbit where eventually you could get further away from the Earth, where you have much more potential energy. The potential would be then to fall back towards the Earth and rocket around and whoop around more quickly on the side than you had before. Okay, if you want to exit the Earth's orbit or get to the moon, right, you fire your rocket thrusters so much, they have so much energy that you can go out on this very elliptical orbit towards the moon. All right, any questions about planetary orbits or any kind of orbit or orbital trajectories? So another consequence, so Newton, when he came up with Newton's laws, and of course he invented calculus in order to be able to do this work, and he came up with his 3 laws of motion, but also the law of gravity. He deduced all sorts of amazing things, right? So he deduced, for example, as I said, the moon is just falling towards the Earth. It's just gravitationally attracted to the Earth. And he explained the motion of the moon, not as being on some fixed circular sphere like the Greeks thought, but it's just falling towards the Earth. But it also has motion, so it kind of keeps missing the Earth, and it's just in an elliptical trajectory around the Earth. And then the Earth, in turn, is in its own trajectory around the sun. So that was one consequence he understood as a consequence of his new reformulation of how orbits come about. They come about from just mutual gravitation. And another one of the deep insights he had was to explain the tides. This is another thing that people have noted for thousands of years, was that twice a day the tides go in and out. Okay, that is, if you're on the kind of coast, twice a day there'll be a high tide and a low tide. And in some places it's just a little bit different, just a few inches. Sometimes it's many feet. Okay, and this is explained in relationship to the moon, and we'll also talk about the sun. The sun is also important for tides. That is, so tide is the rise and fall of sea level caused by a combination of the moon's gravity, also the sun's gravity. So the sun, about half of the effect due to the moon is due to the sun. And we'll also talk about Earth's rotation. So the Earth is rotating, so it kind of sweeps up against the oceans and causes them to kind of rotate around too. And we'll explain the reasoning here, but that Isaac Newton derived that tides are the result of the gravitational effects of the moon and the sun on the Earth. And then a couple hundred years later, people began to actually be able to calculate and use that to derive, on various coastlines, exactly what the tides will be successfully. So it's actually incredibly useful for people to know not only when the tides will be, but how high and low the tides will go. So let's explain this. So if you take Newton's law of gravity seriously, this is the law of gravity. It says that the further, so first of all, the moon is exerting gravity on the Earth, and the Earth is exerting gravity on the moon. The force of gravity is given by Newton's force law here. But what does that force law say? That says that the further you are from the moon, the weaker the gravity is, right? So if we look on the side of the Earth facing the moon is tugging most strongly on that side of the Earth, right? Because that's closer to the moon. So the force of gravity is stronger from the moon on the Earth. So if you have something that can move around like the oceans, the ocean on this side of the Earth is going to be tugged toward the moon. And that's going to generate a high tide facing towards where the moon is. Okay, but we also see a high tide on the opposite side of the Earth. Well, that's for the same but sort of opposite reason. On the opposite side of the Earth, the force of gravity is weaker. Okay, so that is that this side of the ocean is less attracted to the moon, so it bulges in the other direction. Okay, and if the oceans are bulging this toward and away from the moon, then because there's only a finite amount of water, you get low tides on the sides of the Earth facing tangentially to the moon. Okay. So what this tells us, so remember the moon orbits once a month, but meanwhile, every 24 hours, the Earth is rotating. So every 24 hours, if you're here, you get a high tide, then 12 hours later, you get another high tide. So every 6 hours, so if you're here, you have a high tide, 6 hours later, you get a low tide, 6 hours later, you get a high tide, 6 hours later, you get a low tide. So every 24 hours, you get 2 high tides and 2 low tides as you move underneath these bulges pointing towards the moon. Now, the high tide actually isn't exactly the same every day. So the high tide 15 minutes later every day. Why is that? That's because not only are you rotating around every 24 hours, but as we talked a lot about a couple lectures ago, the moon is also orbiting the Earth once a month. So that means you take one, for one day out of 29.5 days, so over 1 month, that corresponds to a change in time of 50 minutes. So every day the moon moves relative to the previous day's high tide by 50 minutes. Okay. And that's just because every day the moon advances a little bit further in its orbit around the Earth. Okay. So we're beginning to understand there's two high tides each day, 2 low tides each day, and each day the times all shift forward by about 50 minutes. So here's just an animation of that, right? So one day and then the next day moon is shifted. So now the high tide is 15 minutes later in the day. Okay. But additionally, the exact same effect happens from the sun. Now, the sun, of course, has much stronger gravity than the moon, but the effect is weaker because it's so much further away. So in total, its effect is about 50%, but it has the exact same effect as the moon. That is, whichever side of the Earth is facing the sun has a bit of a bulge towards the sun, and whatever side is facing away from the sun has a bit of a bulge away from the sun. And so you can have 2 possibilities. Have either the moon is aligned with the direction of the sun, so the 2 effects add, okay? And those are called spring tides. That is, you have really, really strong tides because the moon is aligned with the sun. That is, you have a full moon or a new moon is going to correspond to the strongest tides. Those are called spring tides. Okay? It doesn't have anything to do with the time of year. Okay. Similarly, you can have the opposite. You can have them opposing each other. That is, the sun is trying to pull the oceans one way, the moon is trying to pull the oceans another way, and that's called neap tides. That corresponds to when the moon is half full, so the first or third quarter. So the moon is this way, trying to pull this way, the sun is this way, trying to pull this way, and so they cancel themselves out so that the high and low tides aren't as extreme. So what this says is that the 2 times a month where you have a new moon or a full moon, you have spring tides, very large dramatic change in the tides. The other 2 times a month when you have a quarter moon, a waxing quarter moon or a waning quarter moon, you have neap tides, so the tides are less extreme. So just from this, just reasoning about this, we have a pretty deep understanding of what to expect from the tides. So I'll ask a question based on what we've just talked about here. So got the poll. So based on what we just talked about, at which lunar phases are tides least pronounced? In other words, the tides aren't changing very much. You have the lowest high tides and the highest low tides, just least pronounced tides. When do you expect that?
Think this one.
Maybe 10 more seconds. Yeah, you can't just, the way Zoom works, you can't change the answer to the question after you click it. So be sure. I mean, I always give you a warning, right? I'll say like 10 more seconds. So be sure you are sure before you click. And if it's taking a while, let me know. I can hold off, but looks like almost everyone's voted here. So I'm going to give you 5 more seconds and then I'll end this poll. Okay, so the majority of people said both new and full moon. Okay, so again, the majority didn't get it quite right. So let's go back. So when it's least pronounced. So if we go back here, new and full moon means that the moon is aligned with the sun. So you have the tide due to the sun and the tides due to the moon, both in the same direction, both causing the tides to be more extreme. Okay, what we just talked about the previous slide were called neap tides, which is when the moon is in the first quarter or the third quarter. That is, the moon is pulling the tides this way, but the sun is trying to counteract that by pulling the tides the other way. Okay, so when the moon is first and third quarters, you have the least pronounced tides. People asking if you get the question wrong, does it affect your participation rate? It does. Okay, and that's because a lot of people, I notice, kind of answer randomly. It looks like some people, now I know, of course, a lot of you really are actively paying attention, but some people I think just turn on Zoom and maybe they're playing video games or something, and then whenever a question comes up, they answer randomly or something. So I really want you to get the questions right, and like this case here, right? I literally went over this in the previous slide, and that's so I'm not giving you trick questions here. So I really want you to focus on trying to get the questions right. Okay. So here's an example of a predicted tidal highs and lows at a specific place on Earth, and you can go find these. I mean, we can calculate these at every point along the coasts on Earth. It's incredibly useful. And so here's one place at Friday Harbor here. In particular, places where you have lots of small currents between land masses, like you see here, because the water rushes through those regions as the tides change, you can have really strong effects, like really big changes in the tides. So here's just an example, right? So height in feet. So it's going from, it's changing by about 6 feet here between high and low tide. So that's pretty extreme, about 6 feet change. And remember, that's twice a day. So they're showing low tide separated by 12 hours, high tide separated by 12 hours, 12 hours. Oops. Yeah, the answer was quarters, as described on the slide here. The quarter moons have the least pronounced tides. It's called neap tides. All right. Now, one last thing about tides that has kind of a profound effect on the history on this planet is that Earth's rotation, the fact that Earth is rotating, sweeps the tides just a little bit ahead of where the moon is. There's this picture shows, right? Here's the moon. It causes the tides to be most pronounced in the direction forward and away from the moon. But this bulge is pushed a little bit ahead of where the moon is tugging. And as a result, the moon kind of pulls back. This is called a torque. It's trying to rotate the Earth back towards the moon a little bit, and that has the effect of, over thousands of years, slowing the Earth down, right? Because the Earth is rotating counterclockwise in this picture, but the moon is trying to rotate back clockwise on the Earth, as viewed from the north celestial pole. So Earth's rotation.
I'm sorry, can you make it full screen?
Oh yeah, that's my bad. Yeah, let me know. And by the way, yeah, sometimes people are chatting, but it's much faster to just give me a shout out by audio. Okay. Yeah, thanks. So the moon is kind of tugging back here on the oceans, called a torque, exerting opposite the direction of Earth's rotation. So over thousands of years, Earth is actually slowing its rotation, which means Earth's days are getting longer. So for example, and we can see this in the geologic record, 370 million years ago, for example, the days were 22 hours long, not 24 hours long. And there were 400 days every year. Okay. And going forward,
Get out of here!
millions of years from now, the day will be 30 hours long, and so on.
Get out!
Are there any questions about the time?
How dare you?
Get out of here!
Uh-uh.
I'm in class. Get out! No, you will not. Get out of here!
All right.
I promise.
In the next chapter, this is chapter 5, and this is going to again be a two-part lecture. A lot of material here to talk about light. And light, of course, is how we see anything in astronomy. So this is really important, and it's going to explain basically throughout the rest of the course ways in which we can understand and learn about all the things in the night sky. We look through telescopes with different wavelengths of light. So not just visible light, we'll talk about infrared and ultraviolet and X-ray. And we can use light to tell what kind of elements are there. We can use light to figure out how fast things are moving. Okay, so this will be a really important subject, and I think a pretty fascinating one. So let's start out by just talking about what is light. I mean, this is a question I had. I remember when I was a kid, I was like, Dad, what's light? What is it? It's actually kind of weird because you don't see it moving through the air or through the space, right? You just see it suddenly. You turn on a light, you see the walls get brighter. You don't see the actual light moving around. Anyways, it's if you didn't know anything, it'd be really hard to reason out what light even is. And in fact, there is a totally mind-blowing kind of revolution that happened when someone a couple hundred years ago named Maxwell realized that this stuff called
You're supposed to be in
light,
class, no?
was actually
It's 12:50.
a changing
22,
electric
man.
/ magnetic field. That is, you take like a magnet and wave it. That creates what's called a radio wave, which you don't see with your eyes. But if you wave something fast enough like that, it creates electromagnetic waves, which, if it's fast enough, it literally creates visible light. Light is what we call a wave in an electromagnetic field. So we'll talk more about what that is. We'll also talk about the fact that it has a speed, and it's very, very fast. So if you flip on a light, right, it almost instantaneously
Not in
looks like
here,
it illuminates your wall.
Supposed to go be
That speed is
math.
taken
Come
by
on, get your math book.
speed
The
of
math.
light. 300 million, 3 times 10 to the 8th, 300 million meters per second. Okay, and light can oscillate. These waves that are oscillating can oscillate at different frequencies. That is, they can oscillate very slowly. It's called a radio wave, or they can oscillate trillions of times per second. That's visible light. Okay, and each frequency corresponds to a different wavelength that's given by this Greek letter lambda. And as we'll talk about, they are related to each other, the frequency and the wavelength. By the speed of light is equal to the wavelength times the frequency. That is, If you have a longer wavelength, then you must have a smaller frequency. That's an example of a radio wave. Or you could have a very, very small wavelength with a really, really high frequency. That's an example of, say, an X-ray. Okay, finally, we'll talk about light is actually, when you look very closely, it's composed of particles, okay, called photons. Okay? And each photon has an energy given by this equation. This is just a constant, a Planck's constant. But the higher the frequency, the higher the energy of the light. Okay, so these are the main points that I want to talk about today. So one thing to understand is that there's colors of light that we're familiar with, right? Our eyes can sense some of the electromagnetic spectrum. We'll call it light. But there's lots of types of light that our eyes can't see. And what our eyes can see are the colors red through violet. So shown here, red, orange, yellow, green, blue, indigo, violet. And what you can observe if you shine white light through a prism is that it separates all those colors. And so we've learned now for hundreds of years, we know that there's no such color, there's no type of light that's white light. White is actually just a mixture of all the colors. And in fact, it's our brains that create white light. If you shine all the colors of the rainbow into your eyeballs, your brain creates this color called white, okay? So like the sun, for example, creates pretty white light. If you send it through a prism, you see that it actually creates a rainbow. So the colors from the sun are actually just all together, red, blue, green, violet. And so it's totally a psychological or biological phenomenon, the concept of white, okay? That's not a color. And in fact, if you look closely at a TV screen or your computer screen, now it's hard because computer screens have such tiny little pixels, but you can see that they have like green, red, and blue pixels. And when you look at white, it's just green, red, and blue all together, and it's your brain that creates the color white. Now, what this is showing then, when you look at, say, white light, is that you have different types of light. It's all types of light, and these are corresponding to different wavelengths or frequencies of light. Red light has a longer wavelength and a smaller frequency. Blue light has a shorter wavelength and a higher frequency. And it turns out, if you put like a thermometer up above red here in this picture, the thermometer heats up, even though you can't see anything. That's because next to red, there's something called infrared. Okay. Similarly, next to violet, there's something called ultraviolet. And we understood this pretty early on, even just using prisms, that showed that there are actually parts of the spectrum beyond the visible part that our eyes just can't see. Okay? And so we'll talk about this full electromagnetic spectrum, of which what our eyes can see, red through violet, is actually just a tiny, tiny sliver of all the different kinds of light that you can imagine. Okay. On the left end here, this corresponds to a long wavelength for really low frequencies. We call that radio waves. Okay. The wavelengths can be kilometers. The frequencies can be, say, kilohertz or megahertz, like in what your radio dial shows. Those are called radio waves. If you make a shorter wavelength than that, something in the, say, centimeter range, those are called microwaves. And your microwave oven uses microwaves. Now, the reason those microwaves can't escape the microwave oven and burn your face is because it has that metal grating on the front, and the microwaves are too big to fit through those holes. So the microwaves are about a centimeter wavelength, but each hole is smaller than that, and that's what protects you. That's why you can see into the microwave with visible light, but it doesn't let the microwaves out. We go to shorter wavelengths still. Below, like the width of a human hair, you have infrared. Okay. Shorter still, visible light. Visible light, red is about 700 billionths of a meter, 700 nanometers, to about 400 billionths of a meter, 400 nanometers. Shorter still, we call ultraviolet. Okay. Shorter still wavelengths. Now we have wavelengths less than a billionth of a meter, are called X-rays. And then finally, the shortest wavelengths of light are called gamma rays. So these are all the types of light we'll be talking about: radio, microwave, infrared, visible, ultraviolet, X-rays, gamma rays. And here are the longest wavelengths, here are the shortest wavelengths, and correspondingly, the radio waves have the lowest frequencies, the gamma rays have the highest frequencies. Now, if you look at like visible light, even though it has a frequency, you don't see it flashing on and off. That's because the frequency is so high. It's hundreds of trillions of cycles every second. So it's way too fast for you to see. Any questions so far about the electromagnetic spectrum? Someone asked a question in the chat, but again, it would be helpful if you speak up if you want to ask a question. Okay, so the very first bullet point a couple pages ago, I want to explain what is light. It's an electromagnetic wave. This is profound. It says that something that we had no idea had anything to do with magnetism or electricity is actually just different wavelengths, different and/or different frequencies of waves in electrical or magnetic fields. That is, this is what it looks like. Okay, you have an electric field that increases in one direction and decreases, increases and decreases. That's what's shown in red. It's a wave in electric field. And whenever you have a changing electric field, you have a changing magnetic field. So equivalently, you have an increasing in one direction magnetic field and increasing magnetic field in the other direction, back and forth. That's what's shown in blue. So if you had a compass, the magnetic field would make the compass be waving back and forth, at the frequency of that electromagnetic wave. Okay, and there's this formula that says the speed of this wave, which is the speed of light, it's always the same for every type of light, is the frequency times the wavelength. Okay? So it might oscillate at, say, 1 cycle per second. That'd be a radio wave. That'd be its frequency. But that frequency times its wavelength, how long the wave is for it to complete one of these cycles, that's always the speed of light. That's always c, the speed of light. And that speed is very close to 300 million meters per second. So we often just abbreviate it here as 3 times 10 to the 8th, 300 million meters per second. That's a speed. It's very, very fast. As we'll see, though, that's fast on Earth, but it can be pretty slow when we're talking about traveling to the stars or to other galaxies. So the concept of wavelength, I keep throwing around this term, so I should define it. It's the distance over which it takes one of these waves, which we say is periodic, to repeat. Periodic meaning it repeats. Okay, that is, it goes to max, min, max, min, max, min, and the distance from peak to peak, or from trough to trough, or min to min, we call a wavelength. That's just a distance. How long in distance does it take to repeat? The period, this is why it's called periodic. If you have something that repeats in space, it must also repeat in time. That is, it takes time to oscillate from peak to peak, and that time is called a period. So if you look here at how, if you look at a given point in space and you watch how the E field goes up and down, the time it takes to go from max to min to max is called the period. And the frequency is 1 over the period. That is, if you have a longer period, you have smaller frequency. If you have a smaller period, you have a larger frequency. And the speed of a wave is given by the fact that the speed times time. Remember, velocity times time is distance. The speed times the time it takes to go 1 full period has to equal a wavelength. So we look at time t equals 0, go 1/8 of a period, 2/8 of a period, 3/8 of a period. Once we get to 1 full period, the distance we've gone is 1 wavelength. And that allows us to then divide both the period to get speed c has to be the wavelength divided by 1 period. And since 1 over a period is the frequency, we've just derived the fact that the speed of the wave and how fast it's going when it goes 1 period and travels 1 wavelength has to be the frequency times the wavelength. Okay. So if we want to know the speed of a wave of light, all we have to do is multiply its frequency times its wavelength. Or if we know its frequency and we know the speed, of course, it's the speed of light, we can calculate its wavelength. If we know its wavelength and we know its speed, we can calculate its frequency.
So 1 period is 1 wavelength?
So a period is the time it takes for a peak to move 1 wavelength. So here's this illustration. So here's the wave. So that the axis here is distance. So if you imagine this wave like literally in space here, and it's moving with some speed, the speed of light. So here it's moving. Here it's moving at the speed of light. And the period t is how long it takes to go from here to here, or a peak to move 1 full, what we call wavelength. So this is the distance of a wavelength from peak to peak. Period is how long it takes for it to do that. All right, I think that's a pretty good place to stop for today. I don't want to overwhelm you because we're going to pick this up time and continue. So I don't want to give you a little break. Any questions before I let you go? All right. I'll see you Wednesday.
Thank you, Professor.